Hi, my name is Roseanne Hoffman, and this is Tally. In this video, we will be discussing procedures for testing claims about a population mean when the population standard deviation is not known. To start with, we will review some assumptions that need to be satisfied for testing claims about a population mean. The assumptions are that the sample is a simple random sample. The value of the population standard deviation sigma is not known. Either or both of these conditions is satisfied. The population is normally distributed, or n is greater than 30.
Why is it important that we check whether sigma is known or not?
A terrific question, Tally. Since we do not know the value of sigma, it needs to be estimated with the value of a sample standard deviation s. But this introduces another source of variability, especially with small samples. We compensate for this added unreliability by finding p-values and critical values using the t-distribution instead of the normal distribution that we used when we knew the standard deviation of the population. Let us start with an example. Test the claim that for a population of adults, the mean body temperature is less than 98.6 degrees Fahrenheit. Since sigma is unknown, it will be estimated using S, the standard deviation of the sample, based on 12 observations. We will test the claim at alpha equal to 0.05 level of significance. The sample data is summarized as follows. N is equal to 12. X bar, which is the mean of the sample, is 98.39, and S, the standard deviation of the sample, is 0.535. Before jumping to the hypothesis test, let us first explore the sample data. There are no outliers, and based on the histogram and the normal quantile plot, we can assume that the data are from a population with a normal distribution. Whew, we didn't want to have to do the other tests. Using the following steps in this example, we want to go through and do each of the following steps. The original claim
is mu is less than 98.6.
Now, what is the opposite of the claim?
Its mu is greater than or equal to 98.6.
Now, with this in mind, we can compose the hypotheses. The null hypothesis is going to be
mu is equal to 98.6.
And the alternate
is mu is less than 98.6.
Now, this tells us that we have a left-tailed test. Next, we need to identify alpha. And in this particular problem, alpha is
0.05.
We need to calculate the t-value, which would be equal to x bar minus mu divided by the standard deviation divided by the square root of n. In this particular problem, x bar was 98.39 minus 98.6 divided by 0.535 divided by the square root of 12. This whole calculation turns out to be a negative 1.36. Next, we need to identify the critical region. We'll find out that the t-value is equal to a negative 1.796 from table A3. And we're going to find out that the t-value, the probability of a t being less than 1.796 is 0.05. This is what the t-table looks like. So for 11 degrees of freedom, because we had 12 in our sample, we need to be one less, so it's 11. 12 minus 1 is 11. And then we go over to probability of 0.05 in one tail, and we find out that the value is 1.796. But because it's a left-tailed test, it's going to be a negative 1.796. The last item on our hit parade is we need the test statistic, which was negative 1.36. We find that it does not fall in the critical region. And so we are going to fail to reject the null hypothesis. What this looks like from the graph, you can see that the test statistic, negative 1.36, falls here. Our critical t was from here to the left, and we see this is the rejection region, and because it falls to the right of the rejection region, we fail to reject the null hypothesis. There is not sufficient evidence to support the claim that the sample comes from a population with a mean less than 98.6 degrees Fahrenheit. The data does not prove that the mean is 98.6 degrees Fahrenheit. In fact, the mean may well be less than 98.6 degrees Fahrenheit, but the 12 sample values do not provide evidence strong enough to support the claim. Let's try some examples using the p-value method. Let us review the p-value definition because we want to try the p-value method on the same example. A p-value, or probability value, is the probability of getting a value of the sample test statistic that is at least as extreme as the one found from the sample data, assuming that the null hypothesis is true. Using the A3 table, we observe that the p-value is greater than 10%, which is greater than the 5% level of significance. We came up with a negative 1.363. There we failed to reject the null hypothesis. Due to the limitation of the t-tables, we can only find a range for the p-values. However, exact p-values for t-tests are provided by StatDisk, the TI-83 Plus calculator, Excel, and Minitab. Let us visit the same example this time using the confidence interval method. As you recall, we're going to take x bar plus or minus t alpha divided by 2 times the standard deviation of the sample divided by the square root of n. This is going to be 98.39 plus or minus because we're going to add and subtract the error, margin of error, to both ends of the interval. When we do all of this, we find out that our interval is 98.11 to 98.67. For a one-tailed hypothesis test with a 0.05 significance level, we construct a 90% confidence interval. Because the assumed value of the mean, 98.6, is contained with the confidence interval, we fail to reject the null hypothesis. We learned the procedure for testing claims about a population mean when the population standard deviation is not known. Why don't you practice some of these on your own? It's especially important to make sure that you know how to use the A3 table by familiarizing yourself with finding the range for the p-values by doing problems with different degrees of freedom as well as different significant levels. Thank you, and we'll see you again.